So in this video, we're going to take a look at something that shows up periodically, but with a decent amount of frequency in round 2. And that involves, it's a subset of what you would use the hydrazine fuel for, but this video is going to focus specifically on orbital maneuvers. Now, apropos of nothing, this video is put together to go over that concept because sometimes it can be a little bit tricky. Let's cover the idea of why. So, first off, the thing that this video is focused on is having to put enough fuel into your satellite in order to get the satellite to move itself from one orbit to another. Now, this doesn't show up every time in round 2, but it is one that I've had a number of teams that have had issues with, and sometimes very large penalties can be associated with that because if your satellite can't make it to the orbit in the first place, it can't actually do the mission at all. So the first thing to understand is why, because I had students that did a scenario with that, and they were confused. They thought that the rocket, the launch vehicle, more accurately, was responsible for getting the satellite up to its orbit, and they couldn't necessarily see the logic of why the satellite would need to have fuel of its own. So let's talk about that, the concept behind the idea of what we're doing, because I could see why a lot of people would think, well, getting the satellite into orbit is the rocket's job, which is a true statement, but let's think about an example on this. So the example that I've got is here on the page. You can always freeze and read over it, but I'm going to give you a brief rundown of this. Think about the president. The president doesn't do all their work in the White House. Sometimes they go far away on a trip of some kind, maybe over to another country, and then they need to come back. They do most of their traveling on the big giant aircraft, Air Force One. Gives a lot of ability to do things. There's an office that they can use in there, and then they can have quite a few people that they can actually have meetings and get work done while they do that. The plane is very good at going very long distances, but requires a lot of fuel to carry the big heavy payload of a lot of people, a lot of fuel, and a lot of luggage, among other things. The other thing that the big aircraft needs is a large runway, not only to take off, but most importantly, in regards to this, to land. So it's not like Air Force One lands in the driveway of the White House because there just isn't room for that. There's too much stuff over by the White House. And so it lands some distance away at an Air Force base, if I'm not mistaken. Again, security has a lot to do with this. So the plane is really good for going long distances and carrying a lot of material and people along with it so that we can get the job done well, and in that long trip, the president can still get work done. But it can't get the president, for a couple of reasons, straight to the White House. Or if it could, that would require us to clear a lot of space next to the White House and build a giant runway and set up an entire airport system there, even if it's just for the one plane. That's woefully inefficient and honestly just not something that we would be able to feasibly do. So instead, the giant plane does what it does best, going long distances, lands at the airbase, and then we need to get the president back over to the White House. Well, in the old days, they'd hop into a motorcade and then travel along the streets, but that caused, for security, among other things, needing to shut down the streets and all of that. So the most common way these days is for the president to then hop onto a helicopter. Now, helicopters also fly, but here's the big difference. The Air Force One is a big giant plane that requires a lot of fuel and a lot of special things, like, say, a runway, in order to work, but it is very good at going very long distances. It just needs that additional complications. The helicopter is really good at going short distances. It could never go the long distance in order to carry the president over to another country. And on top of that, it would take a really long time. They wouldn't have a more comfortable office. It would be harder for them to get work done. All of these different things. In short, there's one thing that does most of the heavy work and allows us to get an efficient outcome on that, but because of its limitations, sometimes it's easier to have a smaller thing finish things up. I also thought about tying this to the idea of shipping goods from a factory out to stores and then out to homes, that sort of thing. There are a bunch of other examples that you could look at on this, but basically, some jobs require something that is big and powerful and expensive, and sometimes has downsides and limitations of its own, and sometimes it's more useful, if you can, to use something smaller and more efficient. This same idea is used in what we're going to refer to, and I think is commonly used in the actual profession, as parking orbits. So, the idea on this. the launch vehicles, which I usually just call rockets. We usually think of them as rockets, but launch vehicles is the more appropriate term. So while I may be lazy in a number of my things and just call them rockets, launch vehicles is the appropriate. Anyway, they're like Air Force One. They're really, really good at getting big, heavy payloads up off of the ground and up into space. Now, one of the things that surprises a lot of people is, okay, well, but they may only take the satellite up maybe 400 kilometers or so off the surface of the Earth, and then we're talking about moving the satellite from, say, 400 kilometers up to 1,000 kilometers. Well, that's even more of a distance. And while that's true, the launch vehicles require so much fuel because it takes an incredibly large amount of energy to, one, get the satellite off the surface, two, out of the atmosphere. So even if you're just looking at the distances involved, you have to fight your way through the atmosphere on the way up, and that's going to require a lot more fuel as well. And here's the thing that a lot of people don't understand. In order to put the satellite into a safe orbit, a stable orbit in the first place, you can't just send the thing way up into space, and then if the engine cuts out and that's all you've done, it's just going to fall back down to the Earth. The last thing that the rocket needs to do is actually get the thing going fast enough to put it into a stable orbit. That actually requires a really large amount of energy. And that's where we get our parking orbits. Now, usually parking orbits are where the rocket will be most efficient to actually get your satellite up into its parking orbit. And then after that, if that parking orbit doesn't happen to be the mission orbit, but if that's the best place for the rocket to actually be able to leave the satellite off, then a lot of times it will get the satellite up there and speed it up enough, giving all that needed energy to get the satellite safely up into space and keep it there. Then you only need a little bit more, depending on how much you need to move, energy to actually move from one orbit to another. A lot of the energy is just in getting the satellite up into space and putting it into that initially stable orbit. So what we normally do is we use these big heavy vehicles to take the satellite up and put it into a parking orbit, which is a lot like the Air Force Base from the previous example. And then we, instead of having the big heavy rocket with all of the things that it has to maneuver the satellite into its mission orbit, sometimes we just use engines that are often put on the satellites themselves. In fact, most satellites will have fuel and at least a little bit of engines on them to help correct their orbits if they drift over time, which we'll get to in a little bit. Okay. In short, this is a way of us setting up to make a more efficient way to get things into the orbits that we want. So that's the idea behind all of this, so that you understand why we might ask you to do this in a scenario. It's not just to make things more complicated and give you something else that you have to keep an eye out for, though admittedly that is part of the reason that we do it, but this is actually incredibly common in space technology. Okay. The methods. We've talked a little bit about this, but here's where we're going to get into the nitty-gritty on what you're actually going to need to be able to do. So the idea of the parking orbit is it's usually lower, so it's usually going to be below your mission orbit. Now, it isn't always, but that's the most common way of doing it. And therefore, you're going to need to do what I'm referring to as, and I think is the standard term, maneuvers. And that's usually, at least for this part, to raise the satellite or to adjust its orbit to put it into whatever it needs for its mission. This commonly means that you're going to have to adjust the satellite's orbit from being close to the Earth, maybe 400 kilometers altitude, maybe up to, say, 1,000. Now, you're going to need to find those numbers. They're either going to be given to you directly in the mission briefing. Sometimes we do that. And by we, I mean myself and alternatively stellar explorers. So they might explicitly say, your parking orbit is at an altitude of 400 kilometers, and then your mission orbit is at an altitude of 1,000 kilometers. So you might get those directly in the briefing. Or we might give you that information in a more roundabout way and give you a VDF for STK along with that, at which point you would need to go into your satellite. It's most likely going to be in its mission orbit already in the VDF, and you could right-click and go to its properties and adjust from either the semi-major axis down to apogee altitude and so forth, but you can go into the properties of the satellite to find out what your final mission's altitude actually is. But one way or another, you're going to need to know the different altitudes for, say, the perigee or apogee or just the circular orbit itself. And we will usually, going forward, give you a rate on how much fuel it takes in order to change from one orbit to another. Now, I'm not reading directly from the slides here because an idea on that is you could always pause it and read the words on the slide. I've tried to set it up that the words on the slide should give you all the main ideas as well, but I also find it kind of boring for me to just read what's on the slide. So I'm talking you through the logic of it. Feel free to use both, or whichever one works better for you. And this can also be something that you could freeze and use to help you analyze any of our situations. So in this case, somewhere in our briefing, we'll give you an idea of how much fuel it takes for the engine that you have on your satellite to engage in its maneuvers. So the example that I give towards the top is the engine requires 1 kilogram of hydrazine in order to raise the altitude by 5 kilometers. Or the engine can raise the altitude by 1 kilometer with 0.01 kilograms of hydrazine or something like that. Now, the fuel isn't always hydrazine, but hydrazine's a really, really common one and very, very useful for a bunch of reasons. It also, if you dive deeper into it, you'll see how it's different and therefore is a lot more efficient in how we use it with spacecraft engines, as opposed to, say, the launch vehicles, which usually have a large amount of a different type of fuel that they have to burn. Basically, hydrazine is kind of, you can burn it a little bit at a time and get little boosts here and there, whereas with the big heavy engines, you kind of got to burn all of it at once. Again, different efficiencies. Okay, let's see. So my example that I keep mentioning is if you have a parking orbit at an altitude of 400 kilometers and your mission orbit, where you want the satellite to go, is 1,000 kilometers, then you would need to raise the altitude by 600 kilometers. Well, I would take 1,000 minus 400, so I need to go up by 600 kilometers. If I, for example, use the first ratio that I gave above, if my engine requires 1 kilogram of fuel for 5 kilometers worth of altitude raising, then I would need the following. So we've got a blue equation there, 600 kilometers, and I've taken that ratio, 1 kilogram per 5 kilometers. Now, here's where keeping track of your units can be useful. I'm starting with kilometers, and what I'd like to know is kilograms of hydrazine, so I want to put 1 kilogram over 5 kilometers. If I were trying to solve this a different way, maybe if I started with kilograms, and I was using this ratio to find out how much I could raise my orbit by, because there are other ways that we could ask you to analyze maneuvers, then I would want to put kilometers on top and kilograms on bottom. Always look to try and get your units to cancel out. So I've got this here, 600 kilometers. I want to divide by kilometers and turn it into kilograms. The kilometers cancel out and leave me kilograms of hydrazine. Okay, so in order to do this, I would take 600 kilometers times 1 kilogram for every 5 kilometers, and the math on that gives me 120 kilograms of hydrazine. Now that's what I'm going to need to add into the fuel tank of my satellite in order to achieve this orbital maneuver, to transfer my orbits. All right. In real life space operations often require orbital maneuvers. Changing orbits is part of it, though normally that only happens at the beginning or the end of the satellite's life. And I do want to emphasize that. We very rarely ask you to add materials in there for the end of the satellite's life, but one of two things usually happens when satellites get to the end of their functional life. We will either deorbit them, and that requires engines and fuel for them to actually kind of slow down so that they would fall back to the Earth and do so in a controlled fashion so that it doesn't crash, I don't know, in the middle of Chicago or something. But instead, we usually try and get them to crash into remote portions of the ocean where it's unlikely to cause any problems, at least for any humans. And then when it crashes into the water, it might scare some fish or whatever, but it should slow down pretty quickly as it sinks. There is a spot in the South Pacific that is very, very remote that we actually target often with these called Point Nemo. You can Google it and learn more about it if you'd like. The other thing that is also common to do is to set up what's called a graveyard orbit, where you basically push the satellite out of the way to a useless orbit that no one really wants to use for a variety of reasons, or rarely wants to use. And if we don't have the ability or capability to safely crash the satellite back into Earth, it's common for us to move them over out of the way into a graveyard orbit. That's something that happens a moderate amount, but that could also leave the things up in space, and since people aren't using them, we may not be tracking them as well as we would like, so we might actually stop doing that as much as we move forward with the threat of Kessler's syndrome. Once again, things you could Google. Okay, but that's, like I said, changing orbits really usually only happens for most satellites at the very beginning to go from a parking orbit into their mission orbit, as we described before, and that's the main one that you'll actually do, or at the end of their life to deorbit them or move them into a graveyard orbit. Both of those would require large amounts of fuel and take a while to get done. Although most satellites actually have to correct their orbits on a pretty regular basis. Now, we're solving things paying attention to basically the gravitational effect of the Earth, but the Moon also has a gravitational effect on the satellites. So does the Sun, and so does Jupiter, for that matter. A bunch of things in our solar system, they don't have a big effect on the satellites, but they don't have a zero effect. And therefore, over time, satellites can be pulled or nudged out of their orbit. Well, that's the main thing what these maneuvers are actually designed for. So every, I don't know, month or so, they might turn on their thrusters for just a little bit to push themselves back into their correct orbit. Whatever needs to be done in order to keep them functioning regularly. This is also something that happens if you have satellites in low Earth orbit, because, so for example, the International Space Station is only at an altitude of 400 kilometers. Now that's noticeably above our atmosphere, but the way the physics works out, it actually does have some atmospheric interference from particles that are kind of loosely flying off of our atmosphere is a way of thinking about it. And it would slow down on a regular basis. So if I'm not mistaken, I think the International Space Station, as of the recording of this video, does actually fire maneuvering thrusters, I think once a month, to help push them back up, speed them up enough to keep their orbit stabilized. So that's something that has to happen regularly. If you have a satellite that's in low Earth orbit, like altitudes of 200 kilometers, you're probably going to have noticeable atmospheric effects, and you would need to have some fuel on board in order to regularly fire the thrusters to help correct your orbit. That is something that you might see in some of our scenarios. So if you have something where you've got a scenario that is at like 200 kilometers altitude or in that ballpark, you might actually have to add a decent amount of fuel to keep the satellite up in space. And that actually reflects real life. Most of these things in real life are determined not by just the fuel itself or the altitude, but actually going through a more complex calculation using the concept of delta V. Now, you may have heard of delta V before. I'm not going to go into great detail on this because that's a more complex calculation, but it's what actual engineers would be going through and doing to find out how much fuel you would need to execute those transitions. For us, at least as of the filming of this video, all the times that I think I've seen it, it's been mostly, hey, we give you the ratio to represent that additional work, where here's how much fuel you would need to go this much distance, and it goes from there. The other thing that I'll also mention is this idea of having enough fuel to transfer your orbit sometimes applies in round 3 when you're looking at launch vehicles as well. So the skills that you develop here can also pay off in some of the other rounds, not to mention semifinals and nationals. Okay. Well, I think that's a brief rundown of the orbital maneuvers. Hopefully you found that useful. Until next time.